So I've been asked to talk.
Catch up on the
Okay, I've been asked to just take 15 minutes and orient us. Thank you, Jerry and Fona and the Center for Global Justice. Very few of us are passionate about energy for energy's sake. We're passionate about these issues because they intersect with other things we care about: human development, politics, security, avoidance of poverty, and so on. And so what I want to do is just take a few minutes and walk through what I think are 8 interesting intersections that map onto the issues that we'll be discussing in the agenda today, starting with the kind of fundamental questions about development and poverty, and ending with the questions that in some sense are most germane to a university with tremendous excellence in science and technology, which are questions around technological change and how we understand it. So I'm just going to talk about each of them very briefly. First, I want to say something about the relationship between energy and development. There are a lot of ways to look at this. What I'm going to show you here is the relationship between electricity consumption per capita and human development. Human development the Human Development Index is a composite. So this is a composite that weighs health, life expectancy, education, educational attainment, and economic status or income. Gives them those 3 elements equal weight. And so one of the things we see very clearly is there is some kind of relationship between electricity consumption, and this is true, this holds for other forms of energy consumption, and development. You can achieve some level of development with extremely low levels of electricity or energy consumption. As you go up, you can consume a huge amount of electricity and achieve nothing more in terms of human development. One of the open questions in the field, and this has been debated now for decades, is what do we know beyond this correlation? Right? This is a correlational statement. This is not a causation. And you can make decent arguments about causation running in both directions. That basically it's human development that's driving, through normal business practices and so on, the increased consumption of energy. As people become richer, especially richer in the market economy, they can afford the infrastructure and elements of electricity consumption. Or it could be the other way around, that if you injected, at least in a smart way, energy, especially at very low levels of economic development, that you could catalyze broader development. There will be some discussion of that issue in the first panel. One of the other things that we've learned is that at extremely low income levels, the consumption of energy forms is very complex. So I'll illustrate this with a study, a little bit dated, from Kenya. These are household level studies where the horizontal axis here is multiples of monthly wages at $50. So here you have very low income households. Here you have much higher income households. And what you see, and it varies from country to country and even from village to village, what you see is typically at very low income levels, the energy budget, if you like, measured here in gigajoules per year per household, the energy budget is dominated by energy forms that almost everywhere are free. They might not be free in terms of human effort. You might have to walk miles and hours to get firewood, for example, but they're free, and therefore a household that has little or no monetary income can afford them. And as incomes go up, different kinds of energy forms take over. Kerosene, in the Kenyan case, kerosene is used heavily for cooking and for lighting. Charcoal happens to be dominant in the Kenyan market, and then eventually electricity starts taking over. There's very, very important work to be done at the household level about exactly what do people use for energy, what do people use, and what are those different energy forms. Second major thing I want to talk about briefly is access to modern energy. A lot of people say, absolutely correctly, that it is hard to escape the poverty trap without access to modern energy sources. We know a lot, and a lot statistically, about how that access has changed over time. I will again focus on electricity, although one can do similar kinds of analysis where you look at access to the whole range of modern energy forms like kerosene and LPG and so on. So these are regional data over time. So up to 2010 are actual historical data, and beyond that are projections. These happen to be the projections that the International Energy Agency has done. And the vertical axis is population without access to electricity. What's interesting about this? The biggest success by far in electrifying the population since the U.S. rural electrification program of the 30s to the 50s has been in China and East Asia, dominated by China, where the business model there has been rural, especially small hydro projects, largely driven through normal market or local level investment programs, very little direction from the center. Other countries have different kinds of programs. India, for example, right now is in the middle of a massive, more centrally directed effort to try and connect households to the grid, driven by central government funds and to some degree with private market incentives. India, just in the last decade or so, is starting to achieve considerable success in connecting people to the grid, although I will point out that everything in data depends on how the data are collected, and a lot of data sets in this area count as connected if there's one wire that runs to the village. So if the wire's there, then the entire village is connected. There are really interesting businesses that have emerged in lots of places in the world, battery charging businesses where people haul their lead-acid battery to a charging station, charge it up, and then haul it back. That gives you a sense of how valuable electricity is in modern electricity forms. Some of the work we've done in rural China, western rural China, suggests that people are paying more than $1 a kilowatt hour for electricity, for those first few kilowatt hours of electricity that are so valuable if you want to light or watch television or something like that. Those of you who think that the first kilowatt hours of electricity go to lighting the kids' bedrooms so that they can do studying will be in for a shock when you see what actually happens to electricity, where the dominant use quite often early on is a radio and especially a television. There's a big boon to electrification during World Cup season, and that might be a topic worth investigating at some point. I want to say a couple words about what I'll call the bifurcation of modern energy systems. This is a picture of primary energy. So this is the raw energy that gets used by an economy, the primary energy in the United States for 2010. And this is typical of all modern economies as they mature, is that primary energy largely bifurcates into two forms. Energy that gets used in transportation and energy that gets used in electricity. The transportation business is dominated by petroleum with a little bit of biofuels, but you need a microscope to look at that, and most of that is a terrible use of natural resources. That's a topic for another day. In transportation, it is very, very hard, except for heavy rail and heavy trucking, to beat petroleum because of the flexibility and high energy density of a liquid fuel. You don't see a lot of coal-powered airplanes or nuclear-powered airplanes, and that's because petroleum dominates in that market. It helps explain the low price elasticities of fuel in those markets. Electricity is totally different. Electricity is an unbelievably competitive business, and the challenge here is to find alternatives to petroleum and to extend efficiency, and the challenge here is to find ways to let these different fuels compete. And in particular fuels like renewables and so on that have very different characteristics from the dominant fuels, coal, gas, and nuclear and so on, and we'll have a whole panel on that topic later today. I want to say just a word about what's called the resource curse and the transportation side of the electricity systems. Because oil is so dominant and you don't have really any alternatives but for oil, the politics around oil are nasty and difficult and expensive. And they are encapsulated in the problem of the resource curse. And in our transportation panel this afternoon, we'll talk a little bit more about this. But this just illustrates what's going on. What you see here is for the Persian Gulf members of OPEC. So this is a big Saudi Arabia, United Arab Emirates, Kuwait, and so on. What you see over time is the annual oil production from these countries, the horizontal axis, and the price of oil, the vertical axis here. And here you see the building out of the big, especially the Saudi Ghawar oil fields, up and through the first oil crisis, and then you don't see actually any change in total production since then. What you see are changes in price. And because the demand side is so inelastic, very small changes in production can have massive impacts on the total price of oil. And of course, since the volume of money that flows into a country depends on the product of the production level and the price, basically what's happened since the early 1970s is a gigantic revenue management effort for countries that are big oil exporters. It is a huge problem to figure out what to do with the hundreds of billions of dollars that flow into a country that are basically pure rent. When the price of oil is $100 a barrel and your lifting costs in Ghawar now are $6 to $7, maybe $10 a barrel if you do it in a really bad way, that difference between the two, the $90 a barrel, is pure gravy, if you like, and I'll talk more about that later today. I want to say just a word about the relationship between the energy system and climate. Lots of panels are going to talk about this today, so I just want to show you one slide. This is just a data point, or a series of data points. Since 1970 up to the present day, these are all emissions of different greenhouse gases converted horribly, but unfortunately by the standard of 100-year global warming potentials, into common units. what you see is that total emissions are dominated by carbon dioxide produced from the burning of fossil fuels, and that today we now have a world record of total emissions. So over the last decade, we have seen a tremendous growth in emissions. This should have been the period when international treaties and efforts to try and manage emissions have been taking greatest hold, and instead what we see right now is the period of greatest growth in world emissions. That should be sobering, because it suggests that the last 20 years of international diplomatic efforts to do something about the climate problem have essentially produced zero. And we are seeing emissions growing at unprecedented rates, and of course a big structural change in the economy, and I'll just talk a little bit about those structural changes in the economy and what that means for energy. First, you can take these emissions trends and decompose them into what drives emissions growth. And the standard decomposition is to look at four major components. To look at the carbon intensity, so that's carbon per unit energy. Coal is more carbon intensive than natural gas. Nuclear, for all intents and purposes, is zero carbon intensity, as does wind and solar and so on. You can look at energy intensity, so that's the amount of energy that's needed in an economy for a unit of economic growth. You can look at GDP per capita, economic growth, and you can look at population. And this chart here shows you that kind of decomposition leading to the total changes shown in the triangles by decade. So positive and negative. And what you see, and this is standard, is that population growth is cruising along at a couple % per year. There's not very much you can do about population growth, and frankly, in the future, I think we're going to be worrying about not enough people and not too many people. Over time, reliably, economies become more efficient, even if they're not told to. There's a standard, there's an autonomous rate of energy efficiency improvement in economy as people find new ways to use less energy, and as the economy shifts in structure towards services, which are less energy intensive than manufacturing. What you see in the last decade of what's most worrying, I think, is a massive growth, which we should like overall, driven by China and India, and especially China. And even more worrisome is a recarbonization of the world economy. Over long periods of time, the world economy shifts from high carbon fuels like coal to low carbon fuels. The last decade, we have seen the exact opposite, driven by coal in particular in China and India. I want to just say a couple words about trade and the importance of trade. If we had this seminar in 1990, we would not be worrying about international trade. Because in 1990, the industrialized countries basically net imported almost zero in the form of what might be called embodied carbon, energy that was used to make a product that was then moved across borders, like steel. Steel is very energy intensive, aluminum is very energy intensive. When you make it in one country and then you ship it, say from China to the United States, to get the accounting right, you really need to attach the emissions to the actual product that moves across borders. The structure of the world economy in 1990 didn't have, relatively speaking, very much trade going on. The situation today is totally different. The situation today is a large fraction of emissions are now moving embodied in products and services, especially products that move across borders. So much so that countries that have had enormous accomplishments in controlling their emissions, like Britain is thrilled because they've cut emissions 20% since 1990. If you do the accounting right and you look at the emissions that are embodied in products that the British are importing, this is not an anti-British statement, this is true of all modern economies now, you see that that 20% is totally wiped out. So we need to think about our analysis here in terms of international trade to an increasing degree because of globalization of the world economy. I want to say two last things. First, I want to talk briefly about fossil fuel reserves. A lot of people think the problems associated with energy are going to solve themselves because we're going to run out of the nastiest reserves, and that's going to force us through higher prices to go to alternative products. And I just want a memo from the field that is not true. Here are the actual quantities of coal, gas, and oil that have been extracted from the ground in gigatons of carbon. I'm just shifting units. The people who do this work in tons of carbon as opposed to carbon dioxide. That's what's actually been taken out of the ground, so it gives you some sense of scale. This is what we know in terms of actual reserves. So these are booked reserves that are out there right now. We know nothing about the underlying coal resource, which is probably much larger than formal reserves. Here's the situation for natural gas. Here's the situation for oil. We will end the fossil fuel age not because we run out of fossil fuels, but because we run out of tolerance for some of the side effects of fossil fuels, just as people say, the Stone Age did not end for lack of stones. I want to just point out that reserves are a technical accounting term, and the actual resources in the ground, what we think geologically is out there, that if we just were smart enough to find it, are massive, and in particular in the area of natural gas. Last thing I want to talk about, and then I'm going to stop, concerns technological innovation, which really brings it back to the topic of many of the panelists today. And I just want to make one point about technological innovation, which is that we can imagine ideal technologies like ethanol in Brazil, where over time, you can, in effect, see improvements in technology and the technology becomes more competitive. Ethanol in Brazil, originally in the late 1970s, was more than 3 times the price of its competitor oil. But the Brazilians spent handsomely on this technology. They bought down through learning the cost of that. And now ethanol in Brazil today can go toe-to-toe with petroleum. It's a great, lovely case of technological learning. I just want to point out that when you look at actual technologies in the real world, sometimes you see that learning effect where prices start high, and then with cumulative experience, they come down, and we're all happy because we see technological learning. Quite often, here I'm going to pick on nuclear power for the moment, standard fission-based nuclear power, PWRs in particular, what we see is the opposite of learning. But that is true actually in a lot of technologies. So we should not assume that just because somebody's got a good idea in the lab, that as we scale it up, that the technologies are going to improve. And in fact, and here's where I'll end, is we need to have some sense of the relationship between technological improvement and rates of change. Some technologies change quickly because they work inside the same infrastructure. Classic example is horses versus cars. They're competing for a service, transportation, with the same network, roughly, roads, unpaved roads in particular, which created one of the big environmental problems of the early 20th century, which was mud. And as the horses lost out in competition, the cars came in, and the rate of change, these are US data, the rate of change was about 10, 15 years. Very, very fast, because they're working in the same infrastructure. So you can swap out one technology, take the horses off the road, then eat them, basically, is what happened, and put the cars on the road, and then use them to drive around. And we see that happen sometimes. It's happening right now in the case of the US electric power sector, where coal is competing with natural gas and losing because of fracking and so on. The price of natural gas is so low that natural gas plants are being fired a lot more than coal plants. It's a tremendous change that's underway. It's having a big impact on emissions. So that the gas fraction, which used to be relatively small, is now a much larger fraction, maybe 30% last year of total US electric power generation. But that's because we're working in the same infrastructure. Whereas when you're changing the whole infrastructure, things happen much more slowly. And that's the last slide that I'll show, which is since 1850, these are data also for the United States, you can get a sense of how quickly the system can change by looking at which energy sources dominated the energy system. Back in the middle 19th century, the wood economy was in full swing. Wood lost out as we had coal interlinked very closely with the steel-based and railroad infrastructure. Coal then lost out as the oil economy and electricity came in. Rates of change when you have to change an entire infrastructure are much slower, typically 50 to 70 years historically. So that should be a reminder that when we think about the big scale changes that we're going to need to address some of our energy challenges, that those changes happen quite slowly. And let me stop there. Oh, I'm supposed to say one word, which is I'm supposed to talk about the agenda today. The first panel this morning is going to be the collaboratory on soot, where you see a lot of these different issues interacting, and UCSD has really developed tremendous expertise in this area, thanks in particular to the work of Professor Ramanathan. And then in the spirit of bifurcation of energy systems, the next panel is going to look at electricity, and the panel after that on fuel and transportation, transport oil, basically getting off oil, or making oil work better. And then the last panel is going to bring this all home and look at what this means for San Diego.